Hi there, I'm going to talk to you about big O notation. And when we talk about big O notation, we need to go back over a bit of maths as well. So here's a quick recap. So a function in maths relates a set of inputs to a set of outputs. So if we look at this now, here's an expression here, x squared plus 1, and then the f and the n in the brackets denotes that it's a function, and n is what we're going to be putting into that function. So if you put in n being 1, 2, and 3, then the outputs would be 1 squared plus 1 is 2, 2 squared plus 1 is 5, 3 squared plus 1 is 9. So for the set of inputs 1, 2, 3, we get 2, 5, and 9 as our outputs. Now, when we talk about functions, we have different categories. So we have something called a constant function. That's where everything stays the same. So if I asked you to draw y equals 3 and gave you a piece of graph paper, you draw a straight line going across the page. So y stays the same regardless of what the other values are. So that's y equals 3. Now, a linear function will give you a straight line, which is growing like this. So think back to maths and when you do your straight line graphs and you work out your gradient and your intersect. So y equals mx plus c is the equation of a straight line graph. And we can write that like this as well. So f of n here, where a n plus b and a and b are the constants. So that's m and the c there from that example. And you put in some n's, and the n is always times by a constant, which means that it's going to get this continual growth as n gets bigger. You're going to get this coming up like this here, and that's your gradient there. Now, in a quadratic function, you're always going to get a u. It's a parabola shape or parabolic shape. And depending on the constants a, b, and c, then they can't be zero, you will get the graph in different positions around here. They could either be a u going up or a u going down, and different degrees of steepness, so how rapidly it's going to shoot up there, but it will always be a u shape. Now, in this scenario, you can see that you're growing very, very quickly because you're squaring the n each time you're changing the number going in there. So you're getting a rapid growth on your graph there. So how does that relate to programming then? So we use big O notation to talk about how efficient our program is, and when we're doing that, we're looking at how many statements are going to be executed depending on how much we're putting into the program and how much will be our n in that scenario. So have a look at this. So I'm going to talk through a few examples. There's two statements. First statement here, we're assigning these three things to the animals. So in this scenario, n equals 3 here. So we've got 3 things in our list. And we're just going to pop something off the end. So koala will pop out of that. Now, regardless of how long the list animals is, it's still only going to do 2 executions. So we can put in loads of data. It still takes the same amount of time to do. So it's a constant function and has a time complexity of big O, and just 2 in the brackets there. Now, next example, so with same list, so animals equals sloth, giraffe, koala, and we have a loop now. So for animal in animals, print animal. So we have one statement here at the top, and then it's going to loop through, so it's going to do this 3 times. So we're going to have 3 statements plus 1 is 4. Now, if n grows, and we put 4 things in there, it's going to do the 1 statement here plus 4 here. So this is n, and that is the 1 which happens every time. And you can write that as an expression here. So this is done n times, so it's n plus 1, big O n plus 1. What we do for big O notation, we simplify that down and we drop off the plus 1 on the end. That doesn't make any odds in terms of working out how complex it's going to be to run. So we just write O n, so big O and an n there. And that would be our output, sloth, giraffe, koala. Right, so look at the next one. So we have for loop again. Now, animals equals sloth, giraffe, koala. For animal in animals, we're looping through again. The next statement here, we're getting the length of animal. We're going to print how many letters are in animal. So animal has number of letters. So that will say sloth has 5 letters. Then animal starts with animal 0 will output sloth starts with letter S. So we've got one thing happening at the top here, then we've got a loop. So the loop is dependent on n, and we've got 1, 2, 3 things happening within that loop. n amount of times. So it's a linear function, and that gives us 3n plus 1, because there's 3 statements here and plus the 1 at the top. So O3n plus 1. And again, we just simplify that one down to n. So it still stays the same. So we worked out what's happening there, the number of statements, and then we simplify it down in terms of n. And that's what the output would have been. So sloth has 5 letters, sloth starts with S, giraffe 5, giraffe starts with G actually, doesn't it? And going on, going on. Now, animals equals sloth, giraffe, koala. For animals in animals, for I in range 3, print I, print animal. Now, if we consider this one, we have 2 loops now. So for animal in animals, for I in range 3, print I. So we're going to loop through the animals, and then we're going to print I in range 3. So that's going to print 1, then 2, then 3. And then outside that loop, it's going to print the animal. So we've got nested for loops. We have a plus 1 here, 1 statement there. We've got 3 statements here, and then these 3 statements happen n amount of times, and then that one happens as well. So if we add all that up, we get 4n plus 1. So we have the nested loops here, but we still only have a big O(n). It's still a linear function there. It looks more complex, but it's still linear. And that's what the output would be: 1, 2, 3 sloth, 1, 2, 3 giraffe, 1, 2, 3 koala. Okay, now this next example, this is where we step up now. So in this one, I've written numbers 1, 2, 3, 4, 5, and I've done 2 nested loops again, but they're both dependent on numbers here. So they're both dependent on n, the number of things which are in this list. So for x in numbers and for y in numbers, print x, y. So it's going to loop through n here, and it's going to loop through n there. So it's going to loop, each time it loops through 1 and n, it's going to loop through n times here as well. Now this will come out as a quadratic function, or what we call a polynomial function. And the algorithm has a time complexity n squared plus 1. The plus 1 is this statement here. And then we only have 1 statement happening in that double loop here, but we simplify to O(n) squared. So what's happening in that loop is it's looping through x and y. So it's looping through, it starts, x stays with 1, and then y goes to 1, 2, 3, 4, 5. Then x changes to 2. So we'll go 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. Going on until we get to 5, 5 at the end there. So that's what's happening in that one. And as you can see, as n grows, we're going to have an exponential growth in terms of outputs coming from that function. Right, the next one we're going to look at. So if you remember binary searches and binary search trees we've talked about before. So this is a different type of n that we're looking at here. Now, in this scenario, if you're searching through the tree, you're either going to go left or right, dependent on your search criteria. So it might be higher than or lower than in terms of a number, or it might be in the alphabet here as well, that we're searching through things to find what we're looking for. Now, if we increase the number of items, then we start off at the top, we make a decision there, we go left or right, we come down to here, and then we make a decision left or right, and we find our answer. Now, each time we're cancelling out half the things that we're looking at. So we start off having 4 things to look for, and then we make a decision, then we're looking at 2 things, then we make a decision and we found it. And if you look at that again, we've got, in this scenario, we've got 1, 2, 3, 4, 5, 6, 7, 8 things we're looking at, and we half our group to start with, and then we're discounting everything on this side. Then we're halving our group again as we make a decision there. So if we went this way, we'd be discounting everything that side, and then we go down and we half again. So on a binary tree search, we're halving what we're looking at each time. So it's very rapid to find things. So think of this in terms when we talk about like the guessing game. Think of a number between 1 and 64, and you'd start off by saying, is that number higher than 32 or less than 32? And that gives you your half point. You do a binary search and you're cutting down, you're chopping away half of the possibilities each time. This one has a logarithmic time complexity. So this is O log n. Now, this is great in terms of speed of calculation, because it's only increasing very, very slowly and slightly when n grows in terms of time. This one's factorial, so this is the worst you can get. Now, imagine you've got 1 dice and you roll it, you've got 6 possibilities. If you take 2 dice and you roll them both, you've got 6 times 6 possibilities in terms of outcomes. 3 dice, again, add another dice into the mix. You've got 6 times 6 times 6 possibilities. And this is n factorial. So we're going to have, when n goes up by 1, 2, 3, 4, 5, 6, 7, as it's going up, we're timesing each time and by another factor of n. And it's just going to get bigger and bigger and bigger very, very rapidly. Now, if you look in this graph, this gives you this table, this gives you a better indication of what's happening. So we've got n here being 1, 2, 3, 4, 5, 6. Look at n factorial. That goes 0, 1, 2, 6, 24, 120. 2 to the power of n does this. N squared, 1, 4, 9, 16, 25, 36. And then log down here at the bottom. So you can see n factorial is the one that gives you the biggest number, the quickest as these graphs grow here. So 2 to the power of n will grow rapidly, so that will just double each time. So that next step will be 64, 128, and getting bigger. At this stage, it looks smaller now, but it will become bigger very quickly, much bigger than n squared. Okay, now if you draw the graphs of that, this is what it looks like. So n factorial shoots up really quickly. 2 to the power of n goes off. This will come up rapidly as well. N squared, we know, gives us that parabola. N will give us our linear straight line growth, and log n, so this is log base 2n. This is slower, a very, very slow growth. So that's a really good algorithm to have. So in recap, it's all about how efficient your algorithm is, how long it's going to take to execute, and how does this change as the size of the problem changes. So just back to here. So if you've got a program which was going to be executing n squared statements as the program grows, this is the limits really to computation. So these are what we say are programs which we can solve reasonably, but anything above that is going to take too long for your computer to solve. So we just discount those and we look at another way of trying to write that problem, or just accept that we're not going to be able to solve it in a realistic time frame on your computer. Anything down here, these programs will be quick to run. Regardless of how much you put in, they'll be totally computable. This one is on the edges of it, and these ones not. Okay, so that's big O notation.